Hello everyone, this is Punyashri AG from 3rd year EC, NIT Andhra Pradesh. Today we will be looking at the phase and magnitude spectrum of low pass FIR digital filter designed using Hamming window. So our objective for today is to design an FIR linear phase digital filter approximating the ideal frequency response HD of omega is equal to 1 for mod omega less than or equal to pi by 6 and 0 elsewhere. And some of the additional details are number of tabs to be used is 25, window to be used is Hamming window. So typically over here we need to design a low pass digital filter approximating the ideal frequency response, and cutoff frequency over here is pi by 6. Before heading towards the magnitude and phase spectrum of this FIR filter, let us have a look at the designing of the filter. So in case if we had designed an ideal filter, its frequency response would look something like this, where particularly omega c would be pi by 6. On taking its counterpart, that is calculating its inverse discrete time Fourier transform, the signal obtained would look something like this, a typical sinc function, and particularly over here sin pi by 6 into n by pi n. As this impulse response corresponds to an ideal filter, the number of samples over here is infinite in length and the signal obtained is non-causal in nature. These ideal filters cannot be implemented practically because they are non-causal in nature, and we are required to construct a finite impulse response. So the primary task that we have is to convert this infinite number of samples into finite number of samples and to make this signal a causal signal. And how are these things done? By using the windowing function. And particularly over here, we are going to use the Hamming window. The Hamming window is given by 0.54 plus 0.46 cos 2n pi by m minus 1. And over here, m stands for the number of tabs. So the Hamming window would look something like this. Some of the other types of window that are generally used are rectangular window, Hamming window, and many more. And we particularly use Hamming window over rectangular window in order to mitigate the Gibbs phenomena or the ripples obtained in the Gibbs phenomena. Over there in rectangular window, it has sharp edges, but over here, this discontinuity is softened over here. So now the final impulse response that we need would be the product of this windowing function with the ideal impulse response. So our final impulse response would look something like this. So we can see over here that the number of samples is just finite instead of infinite length, and particularly over here 25. But still this signal is non-causal in nature. In order to make this causal in nature, what do we have to do? We need to shift this m minus 1 by 2 samples to the right. That is nothing but we need to delay the signal by m minus 1 by 2 units. And this shifting, time shifting in time domain corresponds to phase shifting in the frequency domain. So now we have the final impulse response. So now let us look at the magnitude and phase spectrum in the frequency domain. So the magnitude response and the phase response of the designed FIR filter would look something like this. Over here, the phase response is piecewise linear, and the magnitude response also, we do not have a sharp edges at the cutoff frequencies. Instead, it fades out gradually. So now let us have a look at the Matlab code for this. So define the number of range of tabs you need, and then the range of frequency. So our first task could be to calculate the impulse response of the ideal filter. Then calculate the windowing function. Now obtain the final unit impulse response by multiplying the windowing function with the ideal impulse response. So once you obtain the final function, calculate its DTFT. And after the calculation of DTFT, as we have time shifted in time domain, we need to have a frequency shift in the we need to have a phase shift in the frequency domain. Once that is done, plot the magnitude and phase spectrum. Thank you.